The topics I am going to cover, my credential as a designer of post-tension bridges, something I strangely call the empty quarter, that's an idea which I throw at you, the explicit equations of prestress for continuous bridge decks. That is, I saw the word history appeared somewhere here, and this is historic in the fact that I made the intellectual breakthrough about 38 years ago. But it's also right up to date, because I think today is actually the world premiere of it being presented. So that is a world premiere presentation bit of history. Try and work out the philosophy of that one. But actually, I'd like to, not to get too hung up on some of the other things, because I actually think that sort of the economic level of partial prestress, which also comes from an explicit equation, will be the thing which I want to get to in due course. I think I've got plenty of time. Do I have to press twice or something, do I? I said my credentials, I'm a designer, and I like to, when it comes to credentials, I just like to keep my mouth shut. But actually, I mean, this bridge is relevant. I joined Arup in 1968. I moved into the bridge group in 1972, when I was sat down next to Robert Benheim, who had recently arrived from the Fresnay organization in Paris, and he was bubbling with everything you can do with prestressing, and it was fantastic working next to Robert Benheim. The first job he gave me was to do the prestressing calculations on this bridge. In my career, I spent quite a lot of time working in steel and things, which you don't mention at a FIB meeting, but there are, you know, I have actually been privileged to work. The earlier ones, I was the person doing the sums. Later ones, I was the person doing concept. I'm not going to show you very many, but it's just a general impression that I've had a wonderful time designing wonderful bridges, and that's my credentials. Which brings me to the empty quarter. This, I mentioned the steel word. This is actually a slide which was part of a presentation I did. Professionally, I've been involved in the ABSI for many, many years, and I was for 5 years, I was secretary of the British group of the ABSI. And for quite a while, I used to go to all the international, the big annual international events. And I've come up with the term empty quarter for a field that interests me, which is design theory. If you go to a big conference and they go over 3 days and there are 4 different halls and everyone gets 12 minutes or something, you get hundreds of papers. And if you sat down and classified them between theory and practice and between structural behavior and structural design, that gives you a 4-way split. And you will find that 99% of the papers fit into the blue. And then there's this black hole, which is the one that interests me, which is what I call design theory. And I'm quite interested to know why no one else is interested in design theory. There are a whole lot of faces here who are obviously interested in prestressed concrete. Can I just ask you by a show of hands, how many of you are academics in the sense that that's your main income? 1. Gosh, okay, I hope we might have a better spread. Can I recommend that you get involved with the ABSI? Because a similar question internationally in the ABSI gets about sort of at least a third or a half academic, and it's a sort of mix between practice and academia. Okay, I mean, part of the reason for the black hole is that academics are embarrassed by the word design, because that's done by messy practitioners. I mean, why? When we get on to discussions, I'd like people's ideas as to why there is this black hole called design theory. What do I mean by design theory? Well, just sort of, to jump forward, these are my explicit equations, mine. They're not all mine. The explicit equations of prestress for continuous bridge decks. They are explicit in the sense that the amount of prestress you need is represented by, the only algebra is on the left. It's rather nice. They're equations where the right-hand side has no algebra at all. I'm rather pleased with that. and they show you how to calculate the amount of pre-stress you need. They're simple equations, so the problem has been simplified to an extensive length of continuous spans of pre-stressed concrete viaduct with a uniform section, although actually most of them apply even without a uniform section, but not quite. And so what am I showing? What is P1? P1 is what traditionally and Eugene Freycinet would have referred to as being live load governed, that where you have quite a large live load variation, that can govern the amount of pre-stress you need in your section. If you think of a pre-stressed concrete section, and my criteria, going back to sort of Freycinet's early days and things, is quite simply no tension. If you have no tension, then the the position of the compression resultant within the section must lie between the top kern and the bottom kern, if you're familiar with the kern concept. The kerns are the generalized version of the middle third of the section. Numerically, you calculate the distance from the centroid to the top kern as being r squared over yb, where r squared is the radius of gyration squared, and yb is the distance of the centroid to the bottom chord, and vice versa for the bottom kern. Can you see the little blips where the kern points are? So if you're not allowed, the rules are saying you're not allowed tension, so that means that the limits are of the stress block in the concrete are a triangle upwards and a triangle downwards. So that means that the compression resultant in the section can migrate anywhere between the top kern and the bottom kern. And you need to provide sufficient force so that that migration times the pre-stressing force matches the live load moment range, and that's what my P1 diagram shows you. And I credit Eugene Freycinet with that. That equation is in his original paper that he presented at the Civils. I'm not quite, I think 1951, I'm not quite sure when he presented in French. P2. Actually, you don't often find that the P1 governs the design. P2 is what often governs the design. And there you have the problem of the dead load being a sort of a dominant effect. So if you look at the variation in behavior from the support to the mid-span, you go all the way from the maximum hog at the support to the maximum span, and that gives you that arrow. I'm referring to this arrow here. That's the full amplitude or double amplitude, however you want to describe it, of the moment diagram. And then how does the section resist this big change? In two ways. Firstly, you have the same change you had previously from the compression going from its top position to its bottom position. How does the section respond to the change from the support to mid-span? And the answer is the compression moves from there to there. The tension moves from the top position of the cables to the bottom of the position of the cables. So the total response, you add the two bits together, and P2, I hope it is self-evident that P2 is then equal to this moment divided by the combined length. Except that that has built into it an assumption that when you load up your pre-stressed box, it reaches its limiting tension at the support and at mid-span at the same time, and of course, in general, it won't. They will, either the support will go critical first, or the span will. But as designers, we know where the cable has to be at the support, we know where the cable has to be at mid-span, but in the quarter-span regions, we've got some freedom. And we use that freedom to generate the balancing parasitic moment that you need to ensure that the support and the mid-span go critical at the same time. Now, working with Robert Benheim in the early 70s, P1 and P2, we knew that. That was absolutely standard stuff. We were doing design and build, tender bids, and we wanted a very quick way of knowing how much pre-stress we needed. And there was an annoying factor, that balancing parasitic moment. We knew that there were conditions when we had what we knew as unachievable parasitic. And the only way, when you had unachievable parasitic, there wasn't a simple equation. You then had to just do a very quick, longhand, detailed profile check. Pre-computer, this was all pencil and paper, which was annoying. Time moved on, and as I got to the end of the 70s, I was pushed on to working in a material called steel, and the delights of steel box girders and medicine rules and other things. But I was sitting on a desk opposite facing me was Peter Keogh, who'd been given the job of doing the pre-stress design for this tie-ho viaduct. You can't really see from this photograph. It's a twin rib viaduct. It carries access roads to one of the railway stabling yards somewhere on the north, in the middle of the north, I can't remember the name, but the middle of the north of Hong Kong Island. But it's twin rib. And he was getting himself into a sort of a real mess because however much pre-stress he put into it, he couldn't get it to work. And he was in a bit of a paddy about it. I was, of course, meant to be doing my medicine checks, which are, it's nice to have an excuse to get onto something else. So from a slight distance, I was actually trying to understand, and I made I had a blinding flash of light breakthrough in understanding what was happening, which is what I then called, my third equation. So we now come to P3. What I realized, and from watching him plotting out the results he was getting, we had computers, but we didn't have any computer screens or plots or something. It was quite crude in those days. I suddenly realized that when you had a twin rib, so the Z bottom was quite small, that meant that the live load, that in the dead load condition, you had to have enough compressive stress at each point along the bottom fibre to cover the live load moment that was going to come at some point in its life. And that meant that every little segment along the bottom fibre had to be shortened by a length based on the live load moment, because there was a stress based on the live moment that you had that was due to come. If the Z bottom was quite small, that stress was quite large. The total effect of all of these stresses all the way along was to shorten the bottom fibre by a certain amount. Because the span is one of many spans, you can't shorten the bottom fibre without shortening the centroid. And then that leads directly to this equation, P3, and my breakthrough was my third equation, to realize that that's the live load moment diagram, and you'll see that my chain dashed line is the mean value of it, because what I realized, the limiting effect was the total shortening of the bottom fibre, and the total shortening is equal to the mean value of the moment divided by the Z bottom times the length, etc. And you get this P3 is the ML bar. I'm not giving you any algebra at all. It's just that mean value of the live load moment divided by the upper kern distance. You have to play around at home on that just to sort of see that is the case. But it just comes out of the fact that if the bottom fibre shortens by that amount, the centroid has to shorten by that amount. The only way to shorten the centroid is to provide a great chunk of pre-stress equal to P3. Now, I throw in with P3, P4, there are certain cases where there's a transition value, and it even gets a bit worse, because P3, in that Taiho case, the P3 was a lot bigger than the sort of expectations that came from his P2 calculation. P4 makes things a bit, in certain circumstances, and there isn't a very clear explicit equation for P4, except it's between P3 and PT, and if you take it halfway in between, you won't be far out. So those are my explicit equations of pre-stress, and they are my picture equations, and I feel quite chuffed with the fact that you have equations without algebra. So I published my third equation as the preliminary design of pre-stressed concrete viaducts in the civils proceedings, June 1982. My colleagues were somewhat baffled by it, and I was a bit pissed off because I didn't think it was that complicated. But anyway, I then had another breakthrough, and my second breakthrough was the picture equations. Now, the picture equations haven't actually been published. I thought it would be nice to publish them in the FIP, as it used to be. But I hit a snag there, which it's taken me 30-something years to overcome this snag to get me here tonight. I thought it would be nice to present to the annual event of FIP, so I sort of sent off my abstract. But it turns out that FIP prescribes in advance the topics which are going to be discussed in any one year. How the hell do they know who's going to make which breakthroughs in any one year? It is so bloody arrogant and crass that they should do that. If FIP/FIB is a learning society, then it must have an open session each year where people who've made a breakthrough can make their presentations. You shouldn't be limited to whatever someone thought was the topic of the year. Otherwise, because I for 3 or 4 years, I just submitted each year and I just picked up all the rejection slips and then I got bored. And I've waited till tonight to overcome my anger. And aren't you lucky you're here to receive it? Okay, so, why are explicit equations important? Well, the point is, once you've got an explicit equation, you can do things, you can actually differentiate it. I just throw that this is a figure from my civils paper, and it shows that I rather liked on the right-hand side, dP3dA. That is the calculus of shape. That shows you that if you add a unit lump of area at each level up the section, it shows you where it reduces the amount of pre-stress you need and where it increases the amount of pre-stress you need. It's a small step to turn that dP3 into a cost function. You can, once you've got explicit equations, you can put them in spreadsheets, you can juggle things, you can learn a lot. What I really want to talk about this evening is a paper on partial pre-stressing. And this is something, really, it was me trying to get to grips, reading the Eurocode, and trying to see how Eurocodes were going to change bridge design. So the title doesn't include the word partial pre-stressing. It says the design of concrete box girders to Eurocodes. And the significant point is that the Eurocode allows any level of partial pre-stressing, but only with external pre-stress. So which level is most economic? And I'm not sure that anyone else has addressed that. Many designers have felt more comfortable continuing to use internal pre-stress, although they choose to ignore the clause which requires decompression to be checked in all directions. They fail to apply transverse pre-stress. I'm a bit out of touch. I've been retired for many years now. But I suspect that people have a habit of not reading when new rules come out, people have a habit of not reading new rules because they know the old ones were perfectly good anyway. So my little breakthrough here was the moment stress plot. As a designer, it's absolutely sort of crucial how you display data. In fact, a large part of, if we managed to fill the empty quarter, it would be filled with papers that showed good ways of displaying data in a way which makes the design obvious, if that makes sense. So I don't know quite how I fell upon the idea, but I thought I landed up visualizing this in my head. if you have a moment going upwards and you plot stress to the right, and this is talking about partial pre-stress, so you identify that, these dots represent design limit states. So at ULS, there is a ULS design moment applied, and there is a ULS stress at which the reinforcing steel can go to. And then similarly with SLS, and similarly with the quasi-permanent version of SLS as well. So these are the requirements that come out of your analysis. This is a guessed amount of pre-stress. You have a moment. G1 and G2 are a measure of the amount of pre-stressing steel for G1 and reinforcing steel for G2. Oh, why is it doing this? It either goes, yes, all right, good. So that shows you that G1 is the A1, the area of the pre-stressing steel times the lever arm. The point of this is, it's not a big point, but that you don't have quite the same lever arm with the box. And I've gone for a box girder because I'm cheating, because to make life easy, I'm assuming that the lever arms stay constant, so I'm ignoring the web width, just to make life easy for myself. Okay, so to get some feel for what is the optimum, you do the obvious thing. You sort of change the amount of pre-stress moment, and then that gives me, so I come up with the total cost of reinforcement and pre-stressing per meter of deck is increased by that expression. This will be positive if the sigma L, I am just considering sigma L is just a notional limit state, and that's the stress limit for the limit state. So I then land up with these figures, this expression, sigma L is, as you see there, this will be positive if sigma L is less than that expression. If you set sigma L to that expression, that then becomes the balanced value of sigma L, which I call sigma B, and sigma B has that expression which, throwing in some rough typical values, gets me somewhere around 250 megapascals. And now this is the little game that I apply. Having identified that sigma B is at 250 megapascals, it then becomes the vertical red line. And I then imagine that the blue line is a stick which is being brought down from above, and where it hits the red line, I'm trying to get it as low as possible. So, but it can't go past any of the limit state points. So you see that it automatically selects the ULS and the QP points as being the ones that govern it. So, I mean, that bit of algebra is simply just saying that that you've got a straight line going from the ULS to QP point, and where it hits the axis, that's algebra. It's just saying that, and so that is the MPE, meaning the economic value of the pre-stress moment. If I divide by A1, I get PE. It's just that I've given you P1, P2, P3, and P4. So I've given you, here's your fifth explicit equation. You get your value for money. And then with typical parameters, PE is negative, indicating reinforced concrete. Now that was a surprise. I thought we were talking about partial pre-stressing. When the live load dead load ratio exceeds 0.41. Even if this ratio is not exceeded, the quantity of pre-stress will be small, which will raise the unit cost, and again, RC will be the economic solution. This is the end to Eugene Fresnet's concept of pre-stressed concrete as a solution to the SLS deficit of RC. With the current Eurocode, there is no SLS deficit. I think that's a mistake. So, goodbye pre-stressed concrete. Well, we'll come to that. I mean, this makes me uncomfortable. I do not believe that a design and build contractor should be building repeating 45-metre precast spans for a railway viaduct in reinforced concrete. Either my argument has a flaw in it, or the code is wrong, and I'm pretty sure it's the code that's wrong. I'm told the French national annex is more likely to result in a positive PE. I think this is the way to go. Just a bit of historic context. The Eurocodes were launched 2010, as I remember. That doesn't mean to say that they were written in 29. These significant parts of the Eurocode were written in the 1980s. Now, as I told you, in the 1970s, I and everyone else was busy churning out pre-stressed concrete bridges. And then the pendulum started to swing to steel. The steel fabricators invested in numerical control, and suddenly the prices went shooting downwards, and concrete couldn't compete. One way in which the people writing the rules we're using today were writing them in the early 80s, and they were really smarting from the way that the steel people had stolen their thunder. So I think they overstretched themselves in relaxing the SLS requirements. And I don't think they should have done. Any questions? Any answers?